Welcome back, and this is our second example about the transient response of second order circuit. This is a RLC circuit with a switch as shown here, two resistors and one independent voltage source. What we'd like to know is that the capacitor voltage VC as a function of time, and the values of the components are shown here. So let's start with the question. The question is, determine the capacitor voltage for time larger than 0. So what we did, as in the previous examples, we will look at the situation for, first step is the situation for what happened before the switch closed, so for time less than 0. Now in that case, we assume that the circuit is running for a long time. That means actually that the inductor can be modeled and will be modeled as a short circuit, and the capacitor will be modeled as an open circuit. So actually what we have is the following circuit configuration. This is actually the situation. We will use this to determine the required values. So this is the IL for 0, and this is the capacitor voltage for 0. So what we like to calculate is, of course, the capacitor voltage as a function of time, and for that we need the initial value of the capacitor voltage, and we also need the initial value of the derivative of the capacitor voltage. So this is actually the situation for the initial conditions. So the VC initial, as you can see, there is no current flowing through the resistor, so that means actually the voltage drop across the resistor R1 will be 0, so this will be exactly Vm, and that is actually 24 volts for the initial value of the capacitor voltage. So this is actually a situation we can already designate as situation or condition number 1. For the inductor current, we will also need that in the further analysis. Inductor current here is 0 because the open circuit by the capacitor will not allow the current flow. Okay, that's actually for this situation. We have also the situation for what happens just at switching. So just after the switching, we will denote this by 0 plus. That means just after the switch close, what will happen? Now the circuit will be drawn again to show what will happen. You will have again your independent voltage source, the R1 is in place, and I will draw the inductor and the capacitor to emphasize the change clearly. So what we have is the R2, and we have the capacitor C in parallel. So what we have is actually this situation is the intermediate situation just when the switch closed. So actually what we like to know is the capacitor voltage just after the switch closed. So we can use also the current if required. So let's denote this also in the circuit, and also the inductor current just after the switch closed. And let's denote this point as point X, that will be required in the further analysis. Now for continuity condition, we know that the inductor current, this is a situation we can use. Inductor current at 0 plus is equal to the inductor current at 0, which is 0 amps. For the capacitor, the similar situation holds. For capacitor at 0 plus, we have the capacitor also at 0, which is actually the same, and this for this 24 volts. So actually this is a required value for further calculations. Okay, and if you look at the circuit, we can use the Kirchhoff current law at point X. What do we see? We see the inductor current, IL, at 0 plus is equal to current through the resistor R2. I will denote this by I2 by at 0 plus. And you know, the voltage across that resistor is exactly the same as the capacitor voltage, so I will use that because I would like to have an expression consisting only of the capacitor voltage, so I will already do this, divided by R2, that's actually the I2, and I have the capacitor current, which is the IC at 0 plus. We know there is a formula for the current of the capacitor. IC is equal to C times the derivative of the capacitor voltage. So if I now use this formula in blue and substitute it here, and I will use also the value for the IL at 0 plus and the VC at 0 plus and also the given value for R2, I can come up with the expression for the derivative of the capacitor and evaluate it at 0, because that is actually also the required condition. So I will write it down here. This is also one of the initial values we require to calculate to determine the VC. So what is this? So let's write it down. This is actually IL plus, I just fill in the given formula for IC. So what do I have is the following. I will have C times the VC evaluated at 0 plus, which is actually exact same as 0. So let's write it down. This 0 is equal to 24 divided by 2, that's the value, plus a half times the capacitor voltage at 0 plus the derivative of that. So if you evaluate this, you will get the derivative of the capacitor voltage evaluated at 0 plus will be minus 24 volts per second. And this is actually your second condition you require to calculate the VC, the total response. So I will make this also clear and give this number 2. Okay, that's actually for this part. Let's move on. The next step is determining the forced response, because this is the total response, which is actually a summation of the forced response and the natural response. So we start with the forced response, and then we will also look at the natural response, and we will combine the results and determine the unknown constant. So let's move on for the forced response. And for forced response, we look at the situation when the switch is closed, and we again look at the situation when the steady state condition is satisfied. That means actually again the inductor is a short circuit and the capacitor will be modeled as an open circuit. So let's do that. So I will write down this situation for forced response, and that will give me the, of course, the final value. So final value and the forced response are the same here. So what we have is the following. We have the situation again as Vm, which is in series with R1, and the inductor is modeled as a short, and there is an R2 going to ground, and the capacitor is an open. So what you see is actually the inductor current here is IL infinity, and that is actually the steady state value of the inductor current, and we have the capacitor voltage. So capacitor voltage at infinity is just using the voltage divider rule here, so R2 divided by R1 plus R2 times Vm. So that's actually, if you write it down, you will get 2 divided by 4 plus 2 times the 24, that will give us 8 volts, and that's actually also the required value for the forced response. So that's actually required forced response unknown, so there's actually also 8 volts. So this is actually the one of the parts of the total response. So let's move on to the natural response. That is actually the situation, and during the natural response you disable or you turn off all independent sources. In this case we have only one independent source, the voltage source. It will be a short, and we will look at the situation of the circuit itself. So we will see what kind of behavior, what kind of response the circuit components create. That's actually the situation for the natural response. So let's look at this as a next step. So natural response. Natural response, that means the circuit redrawing, means there is a short for the Vm, the R1 is still in place, the inductor will be shown, and the R2 here is in place, and the C is, the capacitor is also shown. So we have now the situation as shown here. We have the capacitor voltage, and the current can be also shown as here, and the current through the inductor is shown here. And let's make this point again x, such that we can carry out the analysis. Now what we can do is we can already set up the equation such that we have a differential equation here. That is actually the goal for the natural response circuit. We would like to have a second order differential equation for this point. So let me write down the Kirchhoff current law at x, and I would like to have the differential equation in terms of the capacitor voltage Vc only, and in constants, of course, like the inductor and the capacitor C and the resistors. So if you do the Kirchhoff current law at point x, I will get IL will be equal to the current through R2 will be this I2. That's actually again Vc. Let me erase it and go continue with black. So Vc divided by the R2, and I have now the capacitor current running here. And what is the capacitor current? The capacitor current is, I will write it down here, the capacitor current is C times the derivative of the capacitor voltage. So if I do this here, and if I again rewrite this, I will have the following. This is the Vc divided by R2 plus C times the derivative of the capacitor voltage. As you can see, we have already an expression with Vc's almost, because we have also the inductor current here. So I will denote this as formula number 1, and we need also another formula to substitute the IL here, such that we have a second order differential equation consisting only of Vc. So let's start with the KVL here. So let's make the KVL, so the Kirchhoff voltage law. How can we set up this? Now we can use the loop here, so starting from here, this point, and all the way to this point. So we use the R1, the voltage across the inductor, and the voltage across the capacitor. So what I have is the following: R1 times the inductor current, that is the voltage across the capacitor R1, plus the VL, plus the capacitor voltage, and that will give us 0. Now I have again another formula which is handy to use here, which is the inductor voltage is equal to the inductance L times the derivative of the current of the inductor. So I will substitute the blue formula I have given here in here, and I will also substitute this expression in here, and I will also substitute this expression in here, such that we have a second order differential equation. So I will show the first steps. So what we have is the following. So the R1 and IL plus the L times the derivative of the inductor current plus the Vc is 0. And if I now substitute this completely in here, so I make this a formula 2, what do I get? So I will say substitute 1 in 2, what do we get? So let's continue in black. So what you get is the following. You get an expression for the second order differential equation as shown, the LC, the second derivative of the capacitor voltage, and then plus the L divided by R2 plus R1 times the C, and then the first derivative of the capacitor, and then plus R1 divided by R2 plus 1 times the capacitor voltage, and it will be equal to 0. Okay, that's actually after you substitute this expression number 1 in the number 2, and then you evaluate and combine the terms, then you will get this. So if I now fill in the component values which are given in the example, what do I get? So we have the inductance, we have the capacitance, and we have the resistors. So let's fill in what we have. I will have this is 1, this is a half, so I will have the following expression, and I will have also here a 1, and R2 will be a 2, and this will be a 4 times a half. So the first derivative of the capacitance, capacitor voltage, and we have the 4 divided by 2 plus 1 for the last term, and you will have this. Now if you simplify this, you will get the second derivative of the capacitor voltage. So what you have is you have a half, so I will multiply left and the right side of the equation by 2, so I will simplify this, and I will get this, and 5 times the first derivative of the capacitor, and plus the 6 times the capacitor voltage. Now if I now, this is equal to 0, if I now use the operator here, which is if I define the S, that's the Laplace parameter, is the derivative, the first derivative of the capacitor voltage, so the second derivative of the capacitor voltage will result in an S squared, and the zero derivative of the capacitor voltage will result in 1, then I will get the following. I will get S squared plus the 5S plus 6 will be 0. And this will result in S plus 2, S plus 3, that will give me 0. And I can now calculate that S1 as one of the roots is minus 2, and S2 will give me minus 3. And if you see two distinct roots, or two distinct poles, or normal modes, different situations, then we have a response which is called overdamped. So this is one of the response types of the second order system. So this is overdamped response. Overdamped response means actually you have more damping compared to the critically damped. For example 1, we discussed the critically damped. Then we had two roots equal to each other, and this will show a different response which has more damping. The general expression for the natural response formula will be given now. So for this case, because we have two distinct roots, we will have the following. So the natural response will be for the capacitor. So natural response will be, the general form will be A1 times e to the power S1t plus A2 e to the power S2t. And we have already two of the unknowns here, so we can say the natural response will be A1 e to the power minus 2t plus A2 e to the power minus 3t. Okay. Now, since we know that we require the total solution, that is actually the combination of the forced response and the natural response. So the forced response we already have determined here. That is the forced response 8. So this one, 8, plus that will give us the Vc as a function of time, which is the required value. But we need to determine the A1 and A2. And how do you determine the A1 and A2? Therefore, you use the initial conditions we have determined in the first step. These are the determined first step initial conditions. So we will use this, and you will use this. So you will fill in the expression for the total solution the 0, and you will evaluate it at 24, and you will equate it to 24, I mean. And of course, you will also calculate for the condition when the derivative of the expression for the voltage is equal to minus 24. So you will have to carry out the calculation actually also for the derivative. So you need also to differentiate your expression for the total capacitor voltage expression. So let's move on. So let me write down the total solution first. So let's move on here. So what is the total solution? So the total response, that is the step here. So total response, which is Vc, which is the forced response, plus the natural response, and the forced response is independent of time, so I will leave it without without t, and the natural response is of course dependent on the time. So what we get is the following: Vc is equal to, and I have already calculated the forced response was 8, and then plus a1 times e to the power minus 2t plus a2 times e to the power minus 3t. Okay, now I will differentiate this. What do we have? If you differentiate this, you will get now 8. You lose the 8. You will get minus 2 times a1 times e to the power minus 2t, and then minus 3a2 times e to the power minus 3t. Now I will evaluate or fill in 0 in both equations, so I will get the following. I will do that in black, so I will have use this, and this was already calculated as 24. So I already know that. So what do we get? Now we have here, if you evaluate it at 0, you will get 8 plus a1 plus a2. So you will actually get the following. So you will have 8 plus a1 plus a2, and that is of course 24. That means the a1 plus a2 must be equal to 16. This is one of the equations we have developed here, so let's call this equation number 3, and we will again need another equation such that we can determine a1 and a2 uniquely. And that's actually from this equation. Let's fill in here for time equals 0. What you get is the following. You will have the time, I will remove this and move this black, so I will have at 0 I had minus 24. Now let's fill in 0 here. That will actually make this again 1, and these again are exponential terms. So I will get minus 2a1 minus 3 times a2. So I will get this minus 2a1 minus 3a2, and this will be minus 24. So if you multiply by minus 1 left and right side, you will get 2 times the a1 plus the 3 times the a2. That will give us 24, and I will make this the equation number 4. Now there are different ways to calculate this. What I can do is I can rewrite equation 3 such that I can make the a2 in terms of a1. So I can do the following. Let me erase this. I can do the following. Then I can say a2 is equal to 16 minus a1. That's actually from the equation number 3, and I can substitute this in here, so I can get only one unknown. So I will have then the following: 2 times the a1 plus 3 times 16 minus a1 will be 24. Then 2 times the a1 plus 48 minus 3 times the a1 will be 24. So what would you get is the following. You will get minus a1 is equal to minus 24, and that will give us the a1 is plus 24. So that's actually one of the unknowns. Now since you know that, then you will have thus the a2 will be 16 minus 24 will be minus 8. Okay, that's actually, these are the two unknowns we required, and actually now we are done. So we can fill in the total solution, which is shown here. This is the total solution. I will make it in green. So this is actually what we will substitute for a1 and a2. So I will use here a1 as 24 and minus 8, and I'm actually done. So let's do that. So then what you get the following is the, let's do it in blue, Vc as a function of time will be 8 plus 24 e to the power minus 2t minus 8 times e to the power minus 3t. And this is actually, of course, in volts, and this will hold for time larger than 0. And that's actually the whole procedure for calculating the capacitor voltage as a function of time. So again, as a summary, very short, we determine the initial values. Let's zoom out a little bit. So we determine the initial values. From that, we continue to the forced response or the final value, and then we look at the natural response. For that, we disable the all independent volt sources, and then you combine the results and you make a total solution, total response, and you use the initial values in step 1 in the first place, and then you use the initial values to calculate A1 and A2. And that's actually the whole procedure for this case. In this case, we have to overdamp because we have 2 distinct roots. That's actually also important. So be careful which response you choose. So the formula you use depends on actually on the results here. So that's actually also important. So we will continue with other examples showing other responses. So this is our second example. We have shown the overdamped response. In the first example, we showed the critically damped response. In the third example, we will also discuss other responses like the underdamped. Okay. All right. Now, I hope this will clear out the problems for you, and I'll see you next time. And don't forget to share and to like. And take care. Good luck.